Hello, this is section 6.3, and now we're going to start looking at some properties of relations. Last couple of sections were just kind of definition of what a relation is, definition of composition, and how to represent them. Okay, so kind of the main way we saw to represent them is with these digraphs, directed graphs. There are other ways that we're going to look at, but let's now look at some properties. Okay. So in particular, we're going to look at, we'll see, kind of reflexive, symmetric, anti-symmetric, transitive properties of relations. So we're going to start with reflexive property. So we call a relation reflexive if and only if A are A for all A in A. Okay, so let's see what that means. Okay, so basically, let A be a set and R be a relation on the set A. Okay, so a small a is any element in the set. So this notation A, R, A kind of gives you the coordinate points. So what this says that for any element in the set A that forms the relation, then these pairs of elements are in there. Okay, so all the doubles. So basically, these pairs of points need to be in the relation for any element in A. So basically, the ones where both the first and the second element are the same. Okay, so let's look at this example one. So the following relation is on the set A, 1, 2, 3, 4. Which of these are reflexive? Okay, so basically for these relations to be reflexive, all the doubles in the set have to be in there. So 1, 1, 2, 2, 3, 3, and 4, 4 have to be in the relation. Okay, it can't be just some of them. All of them. It says that it has to be for all of them. Right. So relation 1, I noticed that 1, 1 is there. 2, 2 is there, 4, 4 is there, but 3, 3 is missing. So that would be a no because the 3, 3 is missing. Okay, so R1 is not reflexive. All right, let's look at R2. So 1, 1 is there, but the others are not. So that's also not reflexive because 2, 2, 3, 3, and 4, 4 is missing. Okay, for R3, I have my 1, 1, I have my 2, 2, I have my 3, 3, and my 4, 4. Yes. Okay, so because all of them are in there, it fulfills the definition. So that's a reflexive relation. All right. Okay, so R4, I notice that none of the doubles are there, so that's a no. For R5, I have 1, 1, and 2, 2, and 3, 3, and 4, 4. So that's a yes. All the doubles are in there. Okay, R6, none of them are in there, so that's a no. Okay, thus reflexive relation is that you have, if you have an element in the set, you also have to have the coordinate points must take this form, some of them, not all of them, then it's called a reflexive relation. Now, so let's look at this one. Okay, so this example, again, we're given a bunch of relations, but these are on the set of integers. Okay, so we're not given the list of elements in the relation. We're given a set builder notation. That's there. Here's a rule, right? And it's on the set of integers. So the kind of inputs and outputs are all integers, and we're trying to figure out if these relations are reflexive. So let's look at R1. So R1 says it's made out of coordinate points A, B, where the first element is always less than or equal to the second element. So we need to figure out if it contains all the coordinate points that take the form AA. Okay, so basically that means where the first and the second element are the same. Okay, so if I look at my relationship, it says that A is less than or equal to B. So these points would be included in the relation because this A is less than or equal to A. So this would be reflexive. So this is a yes. Okay, let's look at R2. So R2 says that it contains all the coordinate points A, B, where A is bigger than B. Okay, so the first element is strictly bigger than B. Okay, so this would not contain elements where these are equal because A is not bigger than A. So this would be a no. This is not reflexive. Yeah, let's look at R3. So R3 is all the coordinate points such that A equals B or A equals negative B. Right? So you basically will have integers, coordinate points where either the coordinate points are the same or the coordinate points are opposites of each other. They contain all of those. So because it contains all the possible combination of integers where the two elements are the same, amongst others, okay, then it's a yes. Okay, so this would be reflexive. All right. Relation 4 says all the coordinate points such that A equals B. All right, so this relation is only formed out of points of this kind where the first and the second elements are the same. So this will also be a yes, this is reflexive. Okay. Fifth relation, we have coordinate points of the type where A equals B plus 1. Right? So the first element is 1 more than the second element. Okay, so that means that something like this would not be in the relation because the first element is not equal to the second element. Okay, so this would not be a reflexive relation. Yeah, and the sixth one, coordinate points of the type where A plus B is less than or equal to 3. Okay, so reflexive relation would contains all the coordinate points of this type for any integer. Okay, so this relation would not be reflexive because it would contain some of them, like it would contain -1, or 0, 0, or 1, 1. So there's some examples that would sort of kind of follow these rules, but it would not contain things like 4, 4, 5, 5. Right? These would not be in there because it wouldn't fulfill that inequality. So this is no, it's not reflexive because it contains some doubles, but not all of them. Okay, good. So as I said, this set of relations we've seen before. We're going to sort of see through the section as we work through the examples in order to examine these properties that we're learning about. So next example, we want to see if the relation is the divides relation on the set of positive integer reflexive. Okay, so it's kind of another way to describe a relation. It's just by words, right? So let's just kind of look at what this relation means. So relation is going to have coordinate points, divides by relation, A divides B. Okay, so this is kind of what we're talking about. So coordinate points where A divides B, so the first one divides the second one. Okay, so we want to see if it's reflexive for the set of positive integers. Okay, let's see, what's the last one? Positive integers or all integers? Oh, that one on the set of all integers. Good. So kind of watch for this language set of integers means that you have positive or negative. Positive integers restricts it to just positive ones. So just kind of watch out for the domain, because it can sort of fool you a little bit if you're not looking at the whole range of inputs. Okay, it makes a difference. So let's see. So basically, if it's reflexive, it needs to contain all the coordinate points of this type for any a being a positive integer. So basically, we need to check if it fulfills this rule. Okay, does a divide a? Okay, and it's a yes. Okay, so for any positive integer, a does divide itself. So this would be a reflexive relation. All right. Okay, so let's look at the next two properties of relations. Symmetric. So symmetrical relation says let R be a relation on the set A. R is symmetric if and only if, whenever A are B, it follows that B are A. Okay, so this basically tells you that if AB is in the relation, then BA is also in the relation, and vice versa, if and only if. Okay, so if you have a coordinate point in the relation, then its inverse needs to be there also. Okay, so that's a symmetric relation. Okay, let's look at for the anti-symmetric relation. Okay, so this says A be a set, let R be a relation on A, then R is anti-symmetric if and only if, whenever A are B and A is not equal to B, then B are A is false. Okay, an equivalent condition for anti-symmetry is that if A are B and B are A, then A has to equal to B. Right? So anti-symmetric is not the complete opposite of a symmetric relation. Okay, so there's kind of these double points kind of makes them not quite opposite of each other, because symmetric and anti-symmetric both could include the doubles. Okay, so what an anti-symmetric relation is, it says that if AB is in R, then BA, its inverse, cannot be in R. Okay, but the exception is the coordinate points where the coordinates are the same. Okay, so these, if AA is in R, then it can still be anti-symmetric. This is okay. Okay, so it's only if A and B are different. So for A and B are different numbers from each other, if AB is in R, then BA cannot be in R, then it makes it anti-symmetric. Okay, now, so what's sort of difficult with this sometimes is that if you don't have any elements of this form, right, then the relation, it's like, is it anti-symmetric or is it not anti-symmetric? All right, so if this is false, okay, so if this condition right here is false, which means that you don't have any types of these elements in there, then this is anti-symmetric by default. Okay, so then it is anti-symmetric by default. Okay, this is like a vacuous proof case, right? Remember that we have this conditional thing, if P then Q. Like if P is false, then this statement right here is true by default, just what we know about conditionals. Okay, so this kind of applies in this case. Right? So if these elements in here, these kinds of elements are not in the relation, then it's going to be anti-symmetric by like a vacuous argument. All right, so let's look at some examples and clarify this. Okay, so we're looking at symmetric and anti-symmetric relations. Okay, and this, again, it's not just for anti-symmetry. This kind of applies for any of these relations, right? So basically, whenever you kind of give them, if this is in here, then this has to be in here. If that first part is not fulfilled, if that first part is false, if those kinds of elements are not in the relation, then they have this property, you know, sort of by a vacuous argument. Okay, so let's revisit the set of relation that we looked at before. I think it was in example 1. But now we want to determine which of these are symmetric and which are anti-symmetric. Okay, so let's look at R1. Okay, so R1 has these in them. Okay, so for them to be symmetric, it says that if I have any terms AB, then BA also needs to be present. Okay, so if there's any terms in there of this form and its inverse is not in there, then it's not going to be symmetric. Okay, so I guess sort of you kind of ignore the doubles, because if a double is in there, then its inverse is already in there. So you kind of don't need to look at them. You need to look at the cases where A is not equal to B. Okay, so 1, 2 is in there and 2, 1 is in there. So they're paired up. That's great. 3, 4 is in there, but 4, 3 is not in there. Okay, so here's something that breaks the rule. Okay, and 4, 1, right, and 1, 4 is not in there. Okay, so this is not symmetric. Okay, and there's like 2 things that break it. 3, 4 is in, but 4, 3 is not. 4, 1 is in, but 1, 4 is not. Okay, so that means not symmetric. All right, again, not symmetric does not mean the same thing as anti-symmetric. Okay, they're not exclusive. All right, so let's look at R1 again. So we're still looking at R1. Let's check to see if it's anti-symmetric. Okay, so anti-symmetric means that if AB is in R, then BA cannot be in R. Okay, so 1, 2 is in R and 2, 1 is in R, so that breaks the anti-symmetry rule. Okay, so because 1, 2 is in R and 2, 1 is also in R, then this is not anti-symmetric. Okay, so R1 is both not symmetric and not anti-symmetric. All right, let's look at R2. Okay, so R2, I have 1, 1, I have 1, 2, and I have 2, 1. Okay, so this is symmetric. Okay, because 1, 2 is in there, its opposite is also in there, then we're good. Okay, let's look at the anti-symmetry. Okay, so this is not anti-symmetric because it breaks the rule. The anti-symmetry says that if AB is in R, then BA cannot be in R, and this breaks it. This pair right here breaks the anti-symmetry. So this is not anti-symmetric. Okay, let's look at R3. So R3, so let's look for symmetry first. So 1, 2 is in, 2, 1 is in. So that's a good pair. 1, 4 is in, 4, 1 is in. Good, they pair up. All right, again, so you don't doubles. They can be in relations that are symmetric and in relations that are not. They are anti-symmetric, or they could not be there at all, basically, when you ignore them if you check for symmetry and anti-symmetry. Okay, so R3 is symmetric. Okay, we'll check for anti-symmetry. It's not anti-symmetric because it's containing pairs and it's opposite. So this is not anti-symmetric. Okay, let's look at R4. So let's check for symmetry first. So I have 2, 1, but I don't have 1, 2. I have 3, 1, but I don't have 1, 3. Okay, so you don't need to kind of go through all of them. Once it kind of breaks a rule for one pair, then it's not symmetric. All right, let's see if it's anti-symmetric. Okay, so again, we go through all the pairs. So 2, 1 is in there, but 1, 2 is not in there. So that's good. 3, 1, but not 1, 3. That's good. 3, 2, but not 2, 3. That's good. 4, 1, but not 1, 4. 4, 2, but not 2, 4. 4, 3, but not 3, 4. So because for all the pairs in there, the inverse is not in the relation, then you say that, yes, this is anti-symmetric. Okay, and again, I'm asking you to keep in mind the symmetric and anti-symmetric are not opposites of each other. As you've seen in R1, they could be not symmetric and not anti-symmetric at the same time. And there are relations where they could be both symmetric and anti-symmetric. Okay, there isn't one here, but a relation like this, where you have just the doubles, like if you have something like 1, 1, 2, 2, 3, 3. Okay, this would be both symmetric and anti-symmetric. Okay, symmetry, again, if you have a pair of points and the inverse is in there, then it's symmetric. And anti-symmetric, this rules, if you have AB, then BA cannot be there. Only applies when A is different than B. It doesn't apply when they're the same. So this is also anti-symmetric. All right, let's look at 5 and 6. Okay, so R5. Let's see if it's symmetric. I have 1, 2, is 2, 1 in there. It's not, so this is not symmetric. Okay, let's check for anti-symmetry. So 1, 2, but 2, 1 is not in there. 1, 3, and 3, 1 is not in there. 1, 4, and 4, 1 is not in there. 2, 2, 2, 3, but 3, 2 is not in there. 2, 4, but 4, 2 is not in there. 3, 4, but 4, 3 is not in there. So this is anti-symmetric. Okay, so you basically go through all the pairs of numbers where the numbers are different and check to see that its inverse is not in there. And then if for all of them that appear that's the case, then it's anti-symmetric. All right, and R6 is not symmetric. Okay, because I have 3, 4 is in there, but 4, 3 is not. And it's anti-symmetric. Okay, because for the pair that appears in there, its inverse does not appear. The opposite with the numbers that are not the same, so it's anti-symmetric. All right, so that's it for this example. I'm gonna finish this video here. The next example is going to be in the next video.